If you've been watching my previous few videos, then you'll know I'm trying to improve the performance of a T-962A Reflow oven, and as part of that project I've made up an instrumentation board. It's just a bare PCB with some thermocouples attached in strategic locations. I decided to make this video as an extra video in response to a very good comment that was left on the previous video, and that was, are these probes accurate? Now what we're doing is trying to convert the machine to give a temperature spread like this, which are the results from these probes when the board's put through a cycle within the machine. And we're trying to improve this. So far I've got it from this to this, and the comment was, well, are these residual errors possibly calibration errors from the probes? It's obviously a very good point, and I thought I'd address that here, and rather than just a simple throwaway comment, I thought I'd give a bit more information as to how I go about doing this. Now, for the last 30 years I've owned and run a company that develops specialist instrumentation, so this is kind of a day-to-day task in making sure that probes are accurate, and so I didn't include it in the original videos. It never occurred to me that anyone would be interested, but if this is the sort of thing that you're interested in seeing as part of projects, then let me know and I'll make sure I include these for future projects. But the idea here, of course, is that we're trying to get all these points on the board to be heated and cooled at the same rate within the machine, and to do that it's important that the probes themselves are all giving meaningful results. So the way I go about doing this, and there are many ways you could do this, of course, but I've kind of developed a methodology over the years that I tend to follow. And the way I go about it is I will initially calibrate the probes over the range I intend to use them for the project. What I will then do is periodically recalibrate them or recheck them through the project. And when I say recalibrate, I don't mean adjust them. If they've gone out of adjustment, then really I've got to start the process again. They shouldn't really change, and if they do, chances are one was faulty or is failing. It's just really to revalidate them. As part of the ongoing process, what I do is every 50 runs in this case or thereabouts, I will take them off the board and recalibrate them. I calibrate them as a set to make sure they're all giving the same response, because it's the response that's important here. It's really the relative readings we're getting rather than the absolute accuracy that we're looking for. Also along the way, any sharp-eyed viewers may have noticed that on various tests not all the channels are always showing. So if we look on this particular test, in which case they are all showing, so if we look at another one, we'll see that in this case channel 6 is not showing. And the reason for this is because on each run what I do is I insert a separate reference probe, and what I'm looking at there is I will then get two sets of data for the same location. I'll get one from the probe that's permanently attached to the board, and I'll get a separate trace for this additional probe. And what I'm looking for is to make sure that the additional probe, which I calibrate more frequently, is giving the same response as the probe on the board. I don't then include the probe on the board because it's modified by having this attached to it. But because I can then calibrate this very easily every few runs, it makes sure that I'm not being fooled by the probes drifting without me noticing. So that's why there's an extra probe, and I move this around the board for different runs just to check each of the probes I'm using. So you may notice on some of the runs that not all the probes are showing, but it's usually just one that's been omitted because I don't want the results skewed by having this. It doesn't matter if the results aren't the same as the rest of the run because it's not been included in the results, but also I'm comparing it against this probe, not against the others. So the next question is, how do I go about calibrating these? So what I'll do, I'll pop the probes off the board. They are due to be recalibrated. They've had 50 runs since I last calibrated them, so I'll take them off the board and we'll look at the calibrator. and I'll show you how I go about making sure they're all reading the same and that they're accurate. Okay, so this is a typical sort of setup that I would use for calibration. Hopefully you can hear me over the noise of the calibrator. It is quite loud. So the general setup would be one or more reference UCAS calibrated meters. So in this case it's a TTI7. This has a resolution of 3 decimal places, so it's a very high resolution meter. This particular one is UCAS calibrated once a year, and the current accuracy is well within 0.02 degrees centigrade. So it's an extremely precise piece of equipment. Now in this application for the exercise we're doing on the reflow oven, that absolute accuracy is not really relevant. What we're doing here is trying to compare probes relative to each other. The absolute accuracy is not that vital, but if you have a reference meter that's calibrated, then it just adds to the validity of the information that you're getting. I typically use them with at least 2 channels running, so what I can do is look at the 2 channels and then either take an average, or if I know the process errors that we have, then I can use that. Now I happen to know here that with this processor, I mean here the actual calibration drywell, that this will show an average if I take the average of the 2 readings, and that will most closely match the actual drywell values. That's why I use 2 probes. I use the system probe and the drywell block probe. So if we do it, normally we'd have this hooked to the PC and we'll be capturing data automatically. But if we look at the 2 values, we've got minus 19 degrees and minus 20. This is set to minus 20, but that's an arbitrary value. It just drives fairly close to that, but it's the UCAS reference that we use for the actual readings. So that'll give us an actual value, a rough value here of minus 19.5. So I'll take a screenshot of the capture software so we can get a current reading. Okay, so you can see the values here, and they are fairly close, so within half a degree of what we're aiming for. Thermocouples in this mode are not generally particularly accurate at low temperatures, but we are within the acceptable range here, so it can be deemed to be valid. The only reason I go so low when we're looking at a reflow oven that's going to be going up well over 200 degrees is because I want to look at the response of the machine, not just the peak temperature accuracy. And although it won't go down to below 0 or even close to 0, because I'm going well outside the range of the reflow oven, then it gives me some confidence that the intermediate values are going to be accurate. So the next thing we do is we drive it up to the next temperature. So we change the calibrator value. So I'll just adjust this. We'll go up now to plus 20. Okay, so this is now set to plus 20. We just now need to wait for it to ramp up to that temperature. Once it's had time to settle and everything's equalized, then we'll come back and we'll see what the readings are. The values we're looking at on the PC software capture are the uncorrected values, and I'll explain what I do with those once we've got all the values we want to measure. One other point here is that this is not normally the drywell I would use for doing this. I need to go up to about 250 centigrade for this particular application with these thermocouples. This drywell won't go that high, but the high temperature drywells I have are too heavy to bring up into the lab, so I'm just demonstrating here what I would do. But normally I would use a drywell that's capable of going up to plus 650 degrees centigrade, but I will only go up to probably 250. But I'm just showing you here with a smaller unit just by way of demonstration, so you can see the approach that I would take to calibrating any reference sensor that I intend to use. Okay, so the temperature's starting to stabilize. We'll check both channels to make sure we're getting an average reading. And so the average here is about 20 degrees, so we'll take a snapshot, and as you can see, again, we are sort of well within the half a degree that we're aiming for. Incidentally, if you are using a piece of equipment like this, then when it's calibrated, you'll get back a calibration error sheet, and that will include any errors that are detected as part of the calibration process. The calibration process probably won't actually correct the errors, it will just tell you what they are. And of course, if you're doing something particularly accurate, then you will need to include those errors to correct the values that you're seeing on the display. They're so small in this case that we don't need to include them for this purpose. We normally use this for taking much more accurate readings, but for this application then the errors are completely meaningless. They are about 1/50th of the error we're aiming for with these probes. Incidentally, if you did want to do something like this, then it is important to use a meter that will give you sensible, consistent results. The only downside is they are quite expensive. This setup alone with just this dry well and this meter is going to cost you somewhere between £7,000 and £10,000. The probes alone are £1,000 each. So it is an expensive thing to do. You don't need to go to this degree of accuracy for general use, but because I'm doing some investigative work on a piece of equipment, the more meaningful I can be sure my results are, the better. You know, it's going to take tens of hours of testing on the reflow oven, continuously running tests, test after test, to get the results, and that will all be pointless if these probes are giving me erroneous results. So it's better to spend a few hours up front making sure that the data you're going to get is meaningful and consistent, rather than wasting a lot of time and getting results that are meaningless. That's really what the comment was about that was left on the previous video, relating to whether these were potentially errors caused by inaccuracies of the probes, which of course, if I didn't do this beforehand, they could well be. Not only could it make the readings seem further apart than they actually are, but it could of course make them appear closer together than they really are. So if the errors happen to be the high ones here had an error that was lower, or made the values seem lower than they were, then the actual data could be a lot wider. So it is important to get this right before you start doing this type of investigative work. So we've now got the data captured for 20 degrees. We know what the errors are for all 8 probes. So now we'll go up to the next temperature. The temperatures you select are fairly arbitrary in this case, but there are industry standards for various applications. In this case, I'm just going every 20 or 30 degrees. As I say, it's not critical, it's just to give me a good indication whether or not the probes are giving accurate results up through the range. Although we're only really interested in the higher values, in this instance I am looking to see if that the heat cycle is accurate all the way up. So I've now got this set to 50. We'll come back once it's settled, look at the errors, and then go up to the next value. Okay, so we're just settling on 50 degrees. I don't know if this display will actually come out on the video or not, but what I'm looking for is for the second digit from the right to stop changing rapidly. If it's changing less than once every 10 seconds or so, then for this application I would consider that settled. In a real world application that we normally use, then we wait for the units to settle so it's not changing by the second most significant digit more than once every 2 minutes. But bearing in mind that's 1/100th of 1 degree centigrade, so it is a fairly precise reading. So we'll take a snapshot at this reading. I am of course recording the 2 readings we're getting off the reference meter as well, so I can take the average of that, and then once I finish the entire run I can see what the overall error is for the probes that we're actually testing. So I'll now go up to 100 degrees. As I say, this won't go high enough for this particular application, so I'll make this the last one and then I'll transfer these into the actual high temperature dry well. But I won't video that, that's out in the workshop, and it's a bit cold up there today. But the operation is exactly the same. It's just putting the probes in, attaching a UCAS reference, and then stepping it through various temperatures until I've spanned the entire range that I intend to use the sensors over. I have the correction values for the previous run, and in theory the same correction values should work when I do the second run. If they don't, then it's either an error in the way that the probes are inserted into the dry well, an issue with the equipment, or more likely one of the probes has changed characteristics. The other thing, if you're going to do this and it's a high temperature application, it's well worth conditioning the thermocouples first. If you turn them up to high temperatures, they will tend to change their characteristics slightly for the first few runs. So what I did with these, I left them at 250 degrees for 3 hours before I started the calibration process, and that just makes sure that the bulk of the change is going to occur before I start trying to use them. Okay, so I'll let this settle at 100. We'll have a final look at that temperature, and then hopefully that will give you a good idea as to the approach I take to make sure I'm not getting errors with the actual sensors I'm using. Okay, so we've settled to 100 degrees. We'll take a screenshot again, and as you can see, we are still well within our target limits. So this is what I do. I just go through the entire range I intend to use at discrete steps, check the errors, and then when I get to the end of the run, I will make corrections to the probe and then rerun it to make sure that the corrections have worked. Just a final point on this sort of equipment. As I say, accuracy is important. If you don't get this accurate to start with, then all the work you do from that point on could be pointless. And the real purpose behind the comments that was left was that the remaining errors could easily just have been probe errors if I hadn't calibrated the probes. And that's obviously true, and if that is the case, then it would be almost impossible to correct, because whatever you did, if the probes are reading inaccurately, then you would have to try to find some way to introduce actual errors within the reflow oven, which would obviously be fairly pointless and goes completely against the entire purpose of this testing. So as I said, I didn't show it initially because you may have found this extremely boring, but this is the sort of thing you have to do before you start any in-depth investigation, and you have to repeat it periodically through the testing. You can't just do it once. At the very least, do it at the beginning and do it at the end. If the results at the end of the calibration period don't match what you had at the beginning, then obviously you need to review the testing that you've been doing, because there may well be some ambiguity in the data that you got. Also, when calibrating probes, it's important that the equipment is suitable for what you're doing. So these wells are very deep, so if I look at one of the inserts, you can see that the actual sensor goes down a very long way into the block, and that's to make sure that there's no conduction of heat from the outside world or to the outside world when you're trying to heat or cool the probe. And that is important. If you're getting an outside influence, then that's going to vary depending on the ambient conditions, and so if you were inserting this into a reflow oven, for example, the outside air temperature could have a major bearing on this in terms of accuracy if you hadn't taken that or eliminated that as part of your calibration process. So the final part of the process, once the data has been captured and all the errors have been determined, the next step is to create a correction algorithm or correction formula for the individual probes. So there's an example of that here. You can see it's just a simple formula that's used based on the errors that have been detected, and the purpose, of course, is to correct the error across the entire range of the probe. It varies slightly from probe to probe, of course. That's the point of this process. But the idea is you should end up with a reading like this, and in this case I've driven the dry well to 140 degrees centigrade, and you can see that we're well within the correct specification. The actual temperature is 140.3, and you can see that we are well within the range of accuracies that we were aiming for. But more importantly, all the probes are fairly close together in terms of their readings, which means that when we use them to run in the reflow oven, that the discrepancies we're seeing across the board are not due to the calibration of the probes. They are actually indicative of the spread of temperatures we're getting within the oven. So I don't know if you found that interesting or not. Comments welcome. If this is the sort of thing you want me to go over when I start projects, or if you want this sort of detail, then please let me know.